So this lecture is going to cover your planar kinetics for your rigid body, and we'll get into force and acceleration. And we will take a look at the mass moment of inertia of your rigid body. Of course, we'll not truly get into the system of rigid bodies because you can do it, but we'll only cover the concept, theoretical meaning of it. This is just a reading quiz. We assume that you have already read the chapter, but if you haven't read it, that's alright too. This is just talking about what mass moment of inertia is. So when you think about a body, and of course I will cover it in my lecture. So right now, every time you think about the moment, all right, the wording is just making your headache. It's just talking about a moment, moment of inertia. Mass means there is a something, an object or a particle. So this little particle or object, but this time we're in the rigid body, okay, category. So we take it like, a rigid body, there's inertia, means something's going on, something is staying. So every time there is a force, you got the moment, okay. You have to feel with the force. Every time there's a force on a rigid body, that body is either staying or moving, okay. If it is staying, that means the forces cannot be able to overcome that potential energy, okay. It's going to stay at a place. But if the force can overcome the potential energy and it's going to start a kinetic energy in that rigid body, then that body is going to move. But a body at a resting position is going to continue to rest, and we call that the inertia. And a body that is going like to keep going, okay. And of course the external force is going to disrupt that ongoing action of that rigid body. And as we do that, there's a moment, because force causes moment, okay. So when we talk about the moment of inertia on something moving or staying with a particular mass, that is just a measure, we're just measuring the resistance of that body, because it doesn't want to stop. So when a body is going, with a motion, it wants to go, and that's what we're saying inertia. It's kind of like the body is resisting to an external force. Something that's going is going, something that is staying is, it wants to stay, it doesn't want to go, okay. And we're talking about that phenomenon right there. So you got to think it over and over again. And in order for a resting body to move, you have to apply enough force to overcome that energy to keep that object in a position, okay. So, and this is a measure of the resistance of a body to angular acceleration, okay, because we are right now in the rigid body, the second chapter of your planar kinetics. Because when we use this mass moment of inertia, we're dealing with the angular stuff, so the key point is right here, and the term, the wording that we use, instead of a regular moment, there is a mass moment, mass moment. So just try to remember, like, if we talk about the mass moment of inertia, it isn't a regular inertia. We're dealing with the angular stuff, and we call that the measure of the resistance of a body. And this is what we call acceleration, because there's a change, a change in velocity when you try to overcome that motion in a body. It's going to be a little bit hard for you to actually get it, because you still have to read, you still have to please read. So I'm giving you supplement reading. It's not to get by heart, but just to read. You have to read again and again to get familiar with the terms that you use, yeah, in different situations. Right now, I assume that you have read it, but you're not still getting it. Don't worry about it. Every time you see the mass moment of the inertia, you understand that you're dealing with the angular, and we're dealing with something that is moving, something that is resting, is going to resist an external force. Okay, at that time, that body has a acceleration of some sort because there's a change in velocity. Okay, so that's all you have to remember for now. Mass moment of inertia is going to be always, what are they giving? It's always going to be a positive quantity, okay? Because you're dealing with the acceleration, angular stuff, so it can't be negative. Yeah, so it's right here, the key point. This is just showing you application, outside application that you can be able to see. Yeah, so here we have a very, very big flywheel, and that thing is connected to a metal, yeah, cutter. And so that mass, this flywheel mass, is used to help to provide. It means like it's gonna give you a uniform motion, okay, to the cutting blade. So right now you wouldn't understand uniform motion and things like that. All you need to know is there's a flywheel. It's connected to a cutter because that's the function of this machine, okay, and it can move. Yeah. Of course, you cannot move this flywheel in an erratic motion because it's going to be cutting like horribly, right? Things that it needs to. So it's, this wheel got to be made to have a uniform motion. So your cut is going to come out as specifying, right, dimension that you want to cut, and that's what it's talking about, a uniform motion. Okay. Now the question is asking you, oh, what property of this flywheel is most important for this use? Okay, so in order for this, the function of this thing is to cut. Yeah, cut something. It doesn't say anything. Well, it will cut something, and it's gonna cut. Yeah, in a constant way. So that's all you know. Yeah, out of it. So So we have to think about the function of this flywheel. What is it that we can use, yeah? And how can we determine the value of that property? What is it doing? We know that it's cutting. We know that we gotta set it in a uniform motion, so it's gonna cut in the right way, in the way we want to specify. And how are we gonna get that value out of it? Why is the most, right? Why is most of the mass in this flywheel is right here near the flywheel's circumference, right there, yeah? So see, these are just a support. In order for the wheel to stand, we need a support. Yeah, so that's how we built this. It's got to be right there, the mass, because again, the function is to cut. Yeah, so where the blade is right here. So let's take a look at, continue to look at this application. So these are the things that you usually think before you build something or before you run, yeah, a machine. And of course, we'll be using the planar kinetics on these applications. The next thing that we can apply, what we're going to study in this chapter, is this oil pump, right? So there's a rig right here. So there's a crank, yeah, here, and pointing this part of this rig. So we call this little thing, yeah, crank, because we are pumping the oil out of the ground, yeah. And this is going to rotate because this thing is going to go down, up and down, up and down, up and down, yeah. So this crane is really important. It's because it's going to give energy to this rig, yeah. And the rig again is subjected to something called the mass moment of inertia, yeah, something that is resting or staying water, yeah, resist the external force, something that is going, want to keep going. So the setup of this machine, this crank is important because we're going to play with that mass moment of inertia of this rig, yeah. is a place where you're gonna initiate the kinetic energy of this machine so that it can do its function. So again, your kinetic energy is something that is staying, something that is moving. Potential energy is something that is staying. And in order for the potential energy to transfer to kinetic energy, you gotta apply force to overcome that potential energy and start a motion. Okay, so vice versa. So that's where the energy transfer is being manipulated by this part. Okay, your crank. So this is where you will be changing between the PE and KE. KE is called kinetic energy, and then PE is your potential energy. And they are moving. There's resting, moving, resting, and it's going to go back and forth, back and forth. Okay, and every time a resting board has been subjected by a force, right? Here in this rig, we're going to crank it up and down. Yeah, so and the mass moment of inertia, again, your angular acceleration is going to play, okay, in this machine, and it will create the enough kinetic energy to do the function of this pumping, yeah, pumping the water out of the ground. Since we're dealing with a mass moment, or I already told you, every time you see this term mass moment of inertia, it isn't the regular inertia. We're dealing with something angular, yeah. So therefore, everything that is angular has an axis of rotation. Yeah, here look at that. Even the machine design. See, you can see very very clearly. There's a D, there's a C. Yeah, here's a crank, and here look at that A, little A right there, and B at the end. See how is a very you can see the mechanism of a rotation right in here at this point. Yeah, so that's your axis of rotations. So every time we apply the mass moment of inertia and dealing with the angular acceleration, yeah, because you're measuring the angular acceleration happening at this point in this application, of course, you always have to think about the moment of inertia, and you also have to think about the center of mass, because without these things, it's really difficult, yeah, for the machine to be stabilized and functioning in this setup. Yeah, you have to set things up according to their mass, the energy, the potential energy, and kinetic energy that they can transfer back and forth between the potential energy and the kinetic energy. When the machine is working, it is in kinetic energy, yeah, motion. When the machine is stop or rest and hold, right, we are going to transfer the kinetic energy back to the potential energy. Okay, so the machine design in this case is your rig. Your oil pump rig is dealing with the changes in that forces and acceleration, yeah, and angular setup, meaning like there's a rotation involved in at the axis of rotation. Okay, so that's a general picture on where we want to use and to apply this planar kinetics. Okay, in this chapter 17. So you get a big picture. You're not getting the detail yet, but that's okay. Okay, don't get a panic attack. Just go slow. Okay, one step after another. Right now, just try to understand. Hey, I know there's some change between the potential energy and kinetic energy. Something that want to stay, okay, is going to resist the motion. If you have like a apply energy or force to it, and something that is rotating around is going to have a mass moment of inertia when it starts to change from the potential energy G to the kinetic energy. All right, things like that, the basic, you kind of got to get it just by reading it. Yeah, reading your book in here. When you read again, don't go into the book too much and then confuse. Okay, reading is just like read, and of course you think with it, but don't think too much on it. Okay, just read, get the new terms, go slow, and hit the important points. Don't go so much into the narration point of it. Yeah. Okay, so we are in the rigid body chapters. Yeah. So still in the rigid body, we started in chapter 16 with the translation, rotation, of your rigid body, and here we're going to get into it. So here we're going to consider a rigid body. There is a center of mass, and that is this point, which is G in this example, of course. And since you have a rigid body, it can definitely rotate. It isn't a particle, without the sign. So therefore there is a size, a body, so it can rotate and it can translate. So it is free to rotate, and the rotation axis in this example is your z-axis drawn here for you in your diagram, and that z-axis is going to pass this, all right, center of mass, right? So you gotta think about why the center of mass was right here. It depends on the shape and the size and mass of that body, okay? We can calculate it. So your physics 1 and 2 to calculate the center of mass. Right now, just keep it like the center of mass. After we calculate it, it's gonna be right here for this shape, all right? And the size and the mass of this body. Okay, now we're gonna apply a torque, and again, don't like freak out with the word. That's just a force. Again and again, a body that is gonna stay unless you apply an external force that is overcome that energy of stay. Okay, you need an energy to take a position anywhere in the universe. Okay, anywhere in the space. In what we know, in what we know from the human perspective. So anyway, all you have to do is apply a force, and I know that students have an issue with a symbol right there, but just a force. You can make A or B or T, doesn't really matter. It's just there's a body and about the size of this, and you have an axis, you have a center of mass, and we are gonna give it a force to it, and we call that a torque. And why do we call it torque? It's because we're dealing with a rotation force to make this body rotate. Okay, so z-axis, and it's going to start to rotate. So as soon as the body rotate, again, your position change, your velocity change. So you have your velocity, you have your acceleration. It's like a domino effect, So bang, you got acceleration because there's a change in the position, or there's a change in the velocity, angular velocity, and of course the rate of change of your angular velocity is your angular acceleration. So you apply a force to a body about an axis z, where the center of mass G is on its axis, and you push it. It's going to rotate around that axis with angular acceleration. Again, I'll put a little symbol for that. Don't freak out. It's just just a symbol. You can give it E or whatever. Just every time you give a new symbol, you have to just legend it. Say like what symbol you use for what, which meaning, for whatever you want to label. Yes. Okay. So anyway, that's war. That's what is a mass moment of inertia. Because before it is at rest, now you got an external force, which is a torque. That external force overpower the resting energy, so will definitely set this body into a motion, and that motion is rotation. Since you're dealing with rotation, your distance away from the center, all right, to the point of that body, okay, distance will change. When the distance changes over time, velocity will change. When the velocity changes over time, you got an acceleration, and that's what it's talking about. And since we're dealing with the rotation of a rigid body, we give it a name, not a regular inertia, a mass moment of inertia. So now you have two quantities here. I beg your pardon because I'm hungry and eating. So now you have your force, and then you've got your angular acceleration. So every time you apply an external force to something, and that body sets into some sort of motion, and they all come together, position, velocity, acceleration, bang, right? And you get a relationship, because if you didn't apply this force, nothing is going to happen, it's just going to stay right there as it is. So since you apply a force, there comes a relationship between that force and that. Well, how much this forces, okay, what happened to this when they come into contact to each other? It's called relationship. It's like you and your girlfriend or you and your boyfriend, right? If you don't meet, there's nothing happen. When you meet, then there is interaction. Yeah, something like that. And we call equation, right? Equations are just telling you what effect that you get when that two things come together. So here you have your force and you have your rigid body here, and they come together, and that is called relationship. Okay, and that relationship, mathematically, we call it equation. Yes. Why? Because it is balanced before, just staying in one position. The force is the force over there, and somebody apply or something apply and hit it right here. And after they get together, like what is going to be if we put that two thing torque, which is a force, a form of force, and then this rigid body together, and how are they going to interact? They're going to interact this way. That's it. Okay, and we call that an equation. Yeah, and then put some symbol to identify. You have a name, right? To identify you. You even have a number. Your name doesn't count anymore because there are so many same names. So we have to give you a number. It's called Social Security number, right? Counting the people in a country or a region. Yeah, like that. You gotta give a name of that force. There are like a zillion or different force right there. Yeah, different force. So therefore, T or torque. Yeah, equal to, and here you have I. That is your mass moment of inertia. Okay, we call it MMI. You can also just use I, that's okay. Okay, so that's a mass moment of inertia, because if you use I, you're going to confuse with a regular inertia again. so, so that's the reason why you have to give like a new term called mass moment of inertia. Yeah, so it's just the I right there. And then about the x-axis, because we're dealing with the angular, acceleration right here. So this force, it's said, is equal to this and this two things. Yeah. Why? Because number one, the body is staying. I told you so many times, in order for a body to stay where it is, it needs an energy that. Okay? Identified by this. And then after the top hit right here, force hits right here, it rotates. Because it got external, extra, actually, I would say like extra energy. And that comes from whatever the torque comes from, okay? And that is going to rotate this thing, and you got acceleration. See that? Acceleration. So in order for that to rotate in a motion, you need the energy, enough energy to overcome the position, taking, which is your potential energy, position taking energy, and it rotates. So you gotta give extra energy for that rotation motion. Yeah, with that energy, it rotates. With that rotation, you get that acceleration. That's what she's saying right here. So just by looking at it, you gotta understand. Here I applied this here in contact, right? T and this thing in contact. This thing moves. It was before wasn't moving. It wasn't moving. MMI. It moves about what? About this much, right? Angular acceleration. Right now, don't even go into the details yet. Okay, that's what it's talking about. Yeah, of course, we have energy things behind the scene going on, which is not written in the equation yet, but we can derive from there. Yeah. So right now, just say there's a mass moment of inertia about the axis times the acceleration is the amount of force or torque that you gotta give this thing for it to move in rotation. Okay, that's all you need to know. And of course, when students read this, students have confusion because they have no idea what's going on right there. So the MMI of a body is a property that measures the resistance of that body to angular acceleration. Here we go, your confusion. So relate yourself back to the real thing outside, okay? You can pick up an object, yes, and you can even like put a rod or something to a make a dough, and go to the kitchen and get a dough, piece of dough, and put a rod in it, a stick or something, and give it a force, give it a force, um, and rotate it and see, okay? And make sure you connect yourself with the physical, physical stuff outside that you can find at your home, okay? So you can make a rigid body like this, and make an axis so it can, rotate, and give it a force to it, and study that, Um, that's all I was talking about. So MMI is we want to know, how much it can resist to this force, and how much you gotta give in order for that to overcome that potential energy and start to move, yeah. And how much can it move depends on the amount of the force, okay. And that is what we're talking about, our mass movement of inertia. So the rest of the images are talking mass movement is used when analyzing the rotational motion. It's pretty easy because every time you think about it, you're dealing with the rotational motion. Of course, we always analyze all the motion that there is in the world, yeah? We're just bragging about it here. It's nothing. Okay, so let's go to the next one. Now we have a rigid body here. Your axis is right there, yeah? Western rotation. So you center that and go over there. Right here, R is that distance far away, and that just a particle that we pick here inside of that rigid body. And we're dealing with our MMI, which is your mass moment of inertia. Just take it inertia. I don't care about MM. I only take letters inertia for this body, and we're dealing with the rotation. That's all I do. Yeah. In my head, I mean, of course. But of course, to pass a test and a quiz and things like that, I do try to connect what's in my head with what's on the paper. Yeah. But in your head, you can put the knowledge that you collect outside in the way you want to put it in, because that's your brain, how you think. Okay. Because if you force something outside in the way other people think, it won't go into your brain. Yeah. So you gotta translate it in the way you think and put it into your own brain in the way you think. Okay. But again, link what you think with what it is outside, and you will pass all the tests that there is in the world, by doing that. If you force yourself with someone else's term and someone else's understanding, it won't get into your head, okay. And that's what happening, for example, like of course at school. So some professor teach, you never get it because you're forcing yourself how they teach it, not translating what they teach in the way you understand it, okay. So studying or learning or reading, is to do that translation, okay. Because in other words, we call it interpretation or perception, yeah. Okay, so then we're gonna get into detail stuff, So don't freak out with the integral again. It's just like telling you, so we're getting into, instead of this general. Your class is gonna be sticking only here in general, yeah. This one, just listen to it. I'm not gonna ask you. So the MY about the p-axis is defined as this, okay. Why? Because we don't have anything that doesn't take the motion in a very small way. Yeah, like I said, you're not the only people living in the world. There are so many things. Yeah, from animals, plants, cells in the animal, particles all over. Viruses is the highest population in the world that we can't see, but it's there. Yeah, the population of virus is actually far greater than the population of human, and they are pretty much alive, by the way. So anyways, these are also particles, there are gazillion or like non-living particles in the world. Like I already told you, we're using the word, like exaggerated word, like gazillion and billions, all kinds of stuff. So anyway, so therefore the motion cannot be so simple. The motion, it's three-dimensional. Three-dimensional is only how we measure. Dimension means how human measure. We can measure x, y, and then z axis. Of course, we break forces into different directions. So that's why all the confusion and complexity goes into this. And then we gotta, of course, put it and note it down or record it. And you can do it with a bulky English or any other language. You have to use a mathematical language to put so much meaning into a very concise, way. And what are we doing again? It's just giving you the relationship of this thing and that thing. So when you look at it, there's only two things going on. So pay attention. There's only this, which is your MMI, the mass moment of inertia. It's just inertia, I. But we call it mass moment because you're dealing with a rigid body rotation, yeah? So the term is different. We're talking about, hey, the inertia, this staying thing is gonna move with an external force. So when the external force come in, we have a potential to move that thing, okay? So that inertia is directly proportional to the change of that thing. That thing can stay there forever. It gotta change because this rigid body has a potential to rotate, okay, and translate. So right now we're looking at rotation. So this will never be the same at the same position. It will always be ding, 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 changing. Yeah, so it depends on what kind of external. There is no just a single external force. You have all the external forces that there is in the world on it, okay? So therefore, this R will change. It can change a little bit. It can change a lot. It can change abruptly. It can change gradually. It depends on the force you apply to it. Yeah, that's what it's saying right here, okay? Again, your inertia depends on the shape, the size, the mass, and how the whole thing is taking a position in a place, or a space. Yes, and that place right there is determined by the distance of the particle, any particle in that body, representing that body, and then the axis, crossing the center of mass, center mass. All right, on that axis line, in this case is P. Anyway, when you go back here, just think there's a relationship, a body that is about to rotate or move because of an external force, we call it inertia, is related to your position. That's it. Yeah, if you get it, I'll be happy. Because your R, again, since we're dealing with angular stuff, we call it moment. It's just a position actually, the position of this guy away from here. And we call that another term, moment. Yeah. So that thing is perpendicular distance from the axis. We all know that here. See little perpendicular 90-degree sign right there. Yeah. To the element, which is this one. It just this can be anything. Any point. Any little chunk of particle in that rigid body. So mass moment inertia, unit is going to be kilogram meter per square. In British, slug, feet per square, And probably I might ask you this one, a meaning of that, Of course, I'm not going to ask you how to calculate the stuff because you don't want it. So that's all right, We're happy to help you. And mass moment inertia, next one. Getting into, I'm not going to ask you, just listen, listen so you kind of get the general picture of it. So the picture here show you the mass moment of inertia in two different geometry shapes. Look at that. So this thing is circle and that thing is kind of like a rectangular, a little bit square, but not perfect square, rectangular shape right there. Of course, it is. When you pay attention to it, this is not a two-dimensional because I have three axes right here. Dimension means we're just measuring, okay? Measuring from here to here is that much, from there to there is that much, from there to there is this much of this body, okay? That's what we're saying. So every time we want to calculate the exact amount of inertia, your mass movement of inertia, we have to calculate this way. Depends on, again, on the shape. Since we're dealing with a different shape, we have to do integration. That's all it said. Okay, mathematically we cannot solve it with a linear or just a regular algebra. So therefore we use something called integration, is because of the complexity of the shape. Shape is not like a primitive shape. It's just there are many different kinds. Even this is like very primitive shape, by the way. In real life, you have like different surfaces, not a perfect surface like that. And that's what it's talking about. So don't freak out. I will not ask you any of it. Okay. Procedure for analysis. Okay. Again, just listen to it. Not necessary. We'll just stick to what we choose, the selected problem for you to calculate. So this is just how we deal with the moment of inertia, and integration is of course essential. It's because based on different shapes, yeah, rigid body has different shapes, and of course we always deal with the coordinate system, at least three, yeah, measurement, because you can't measure this thing because it has a body with two axes or one, yeah, dimensional axis, or because it has a body, so you still gotta have like height and width and length, yeah, depth, things like that, yeah. So that is what it's talking about. When we do the analysis, we have to pay attention to the shape of the body, yeah, the dimensions of that body, and the movement of that body, yeah, we will consider. And reference point is always the axis, okay? Because without axis, we can't be able to measure them, yeah? Can you? Yeah, you can't. Okay, then well, let's get into the next. Continue the that just going back to your example for your disk element, yeah. So every time you deal with a disk, it is a circle, so you deal with a radius thickness, yeah. And you have little changes, so every time we study the changes, we use derivative integrations, yeah, like that. And that's all it's talking about. So you gotta hit like, oh, I'm dealing with the, yeah, rigid body rotation, and I'm studying inertia, and I gotta pay attention, yeah, if I truly want to get the value right closer to the most accurate value, then I might have to do integration and, yeah, derivative. So you should know that the every equation is giving you the relationship between these quantities, yeah. Quantities come directly connected to the physical stuff outside, yeah. And in this case, you're dealing with something moving about an axis rotation, and I need to have a force to change that inertia, yeah. So if you get about that much in analyzing it, you're okay, yeah. So if I ask you like, oh, analysis of this rotation, what do you have to understand, then you should at least know that if we want to get a value, yeah, for this quantity, that quantity, we've got to use a coordinate system to get it. Why? Because all the forces are breakable into vectors. Yeah, one force is not just force, is that we call that the total force, and that total force is subjected to the sub forces, yeah, oriented in different direction, because a motion is actually the resultant of the external forces, seen or unseen, known or unknown. Okay, so therefore, when you think, you have to think all around 360-degree around, not just limiting only one force. Okay, so the more you think and include everything, then your value will close to the yes, true value. Yeah. So we usually assume, oh, that's the only force on a body, and then neglect everything. So in the problem, you will always see that, or assume this is the only, yeah, assumption. So meaning like we can be able to go into the complex calculation. That's all it said. So anyway, so that's your procedure for analysis. Hit. And at least know that we break it into x's, yeah, to study. We use integration and a derivative to deal with different shapes. That's all you need to know for analysis. Okay, and then got into parallel axis theorem. All right, parallel axis theorem. This is where I talked about, yeah. So even if the equation is going back to the regular equation, this I you will have to integrate to get the final value of it, right? In the exam, I'm going to give you the final value directly, so you don't have to calculate it, okay? So that way you don't need to freak out. So if I give you a value of this and that, I am sure that you're going to be able to add this up. This is just a square, by the way, yeah? So this is a pretty simple equation, so I will definitely ask you this, yeah? And I will give you the value of this, value of that, and you do that, yeah? That you definitely know how to do it. Of course, in real calculation, you will have to find this thing based on the previous equation, integrations, and a derivative. And once you get this, then we calculate that. So this equation is called parallel axis theorem. It's just talking that your mass moment of inertia, okay, is equal to the mass moment of inertia passing through the center. This is called the body, your center of mass. Body center of mass, little g. Remember this little g right there, a point. Okay, so the MMR at that point plus, okay, and then mass of that thing, and then the distance, which is a d, okay, from here to here, the whole square, and thus we call it parallel axis theorem. So what is the D thing? Oh, that's not R. I know only R. What's this D? I don't know, right? So that D is just like the axis to a distance, distant point. We usually just use whatever letter here. Here in this case, we use the A. So that's from the G all the way out to a particular place, and we call that distance D. Okay, and this cutoff point is parallel to your one of the x's in that body, and there are 3 x's every time we study, and that's all they talk about, and that is your parallel axis theorem. So your question is, where are we going to put this A? I don't know. That depends on your problem. Okay, the problem is going to clearly state where that A is. Okay, sometimes you have to find that A. Where is it going to be the A? I don't know. So you will be calculating this. You will know this, and that. Okay. So where can this D be? It can be on that side, it can be on this side. All right? And it can also be on this side, because not only this is one example, picking a z-axis. It can also parallel to the x-axis or y-axis. All right? So there are many parallel axes in this body. So that's what we call a parallel axis theorem, because you can be able to calculate the mass moment of inertia of the entire body from one of them. Okay, so one of the parallel axis. So you can get the MMI of any other axis. You don't have to stick only the one that goes through the center of mass. So if you know the moment, our first initial approach to the MMI is we pick a point, and that is your G, and we measure around it, related to that G. But then G is not the only point. We have all other points that there is in the world around this body. So how are we going to get to that point? So we start getting, okay, we can measure it, by using a coordinate system. So from here to there. See how the point, this A again, can change from here, and then here, Y, here, all the way up. So any kind of point that you can change with this theorem, So therefore, we're going to use this theorem. Hey, I can get the MMI. I don't have to stick to the MMI at G, always. We can get the MMI at any point by applying this method. Yes, so that's how we get the MMI again of moment of inertia, okay, about any other parallel axis. You can determine by using this relationship, because it is related to the MMI at G and the mass of it time at it, mass of it time the distance, the whole square, you time it, okay? And that amount is called the moment of inertia about any other parallel axis. Okay, this axis can be x or y or z. That's all you need to know. How easy that is. Okay, now let's go to the next one. Now we will study a little bit about radius of gyration. Okay, some people read it gyration. It just depends on how you want to pronounce it. So here, inertia, this is not a G, this is at any, okay, about any specific axis. And we're going to use the radius of the gyration, which is another term which is called K, okay? This is called the radius. Don't forget it, radius. Radius of what? Radius of gyration. Why? Because that axis is about a specific axis. that we're dealing with MMI at a specific axis, right? Your XYZ. And then the radius of gyration has units of length and is a measure of the distribution of the body's mass, yeah, about the axis. So don't bog down in here either. Every symbol has a unit, okay? Because we're dealing with a measurement. We're measuring from here to here, here to there, and there to here. Yeah? So therefore, radius of gyration, it has a unit of length, meaning like, oh, just the length unit that we will use, like feet or millimeter or centimeter, so and so. Since you're measuring, you gotta know from where to where are you measuring. So you're measuring, yes, the distribution of the body mass, meaning like every time we think about the mass, we're thinking about the point in that body. Yeah, again, so many particles inside of your body. Don't forget that many particles inside of a rigid body. Yeah, so we call it distribution of the body's mass about the axis. So each particle inside of the rigid body, yes, is measured from an axis, and we're talking about that axis because without the axis you cannot be able to measure where they are, yeah, in the body. So therefore you can be able to get the MMI around about the axis, yeah. So we go deeper into it. So at which the moment of inertia, again, of interest, yeah. So this is where you want to get your moment of inertia value, and that is about a specific axis, and that axis got to be measured because it is standing on a particle inside of that rigid body, and that measurement, okay, is called a distance. So therefore takes the unit of the length, and we're going to give it a K, just like your R, just like your D. It's just a distance. You have nothing but the particle inside of the rigid body, and they are going about rotating about an axis. And since you're rotating, the PE, your potential energy and kinetic energy changes according to the external force. Yeah, so every time there is a change in the motion, whether they're resting and going to kinetic motion or not, right? The particle distant from the axis is gonna move around. So therefore, the position changes, and we are studying that. First, we study the axis that pass through the center of mass. Now we're getting into the axis that pass through any point, whether it's inside of the body or outside. And we measure it with the three major axes, X, Y, and Z. And you are talking about the distance, okay, on the axis. And we give it like a K for that. Your mass doesn't change because it's just right there, yeah? And then, of course, you change it and move this, and move that to here. And then take this square out. So you got the square root of I divided by m. Okay, so if you want to get what is the distance, you always have to measure where that distance is, yeah? When you build the machine or not. So we gotta concentrate where the force is going to be applied to get the resultant force, yeah? Okay, composite body. So if your body is like you have a simple shape, like this, sphere, rods. So these are primitive shapes. So your MMI, okay, of that body, about any axis in there, you can algebraically add, together each one of them. Calculate your MMI and then add them up together. And then all the mass moments of inertia, are found about the same axis of different shapes. So that's what we're getting into. First, we start with a little body with a particle. You gotta just think in your mind that the particles are right in there. Points. We call it point here, aggregation. In the body. Now we're moving up one more step. And that step is kind of like assembly. You have a sub shape and sub shapes like that. This and thus shapes are all combined together and constructed into a bigger body. So the body has a sub shape. So if you want to get the total moment of inertia, mass moment of inertia in that body for rotation, angular stuff, then all you have to just add them up. Add the MMI of the sub stuff. That's all it said. not very accurate, but it's easy to calculate that way. Okay. Example 1, choose this for you. The question is, so here we have a pendulum, and that pendulum has a slender rod right there. Okay, the mass is this much, 2 kilogram, and it has a circular path right here. Yeah, the mass is going to be like 4 kilogram. So 2 kilogram here, from here to here, 4 kilogram here. Yeah, for the plate, circular plate. It is constructed in we call this a pendulum, all right? A pendulum constructed into a pendulum with this rod and this plate. See, 2 parts right in there to build this assembly right there. Yeah, this is 2 kilogram and that is 4 kilogram. We know the mass. Okay, we know the distance, measuring from where, from here to there, and from here to there. Okay, so these are your dimensions given to you. So we gotta find the radius of gyration. So since you're dealing with the radius of gyration, we are not we're not looking for the mass moment of inertia at G, the center of mass. We're looking for the mass moment of inertia, okay, at a distance. So because your problem is asking you, oh, give me the radius of gyration about n axis perpendicular to the screen and then passing through the point O here. Yeah. Okay, so don't worry about this. Okay, so first we know there's a rod, there's a plate. Okay, and we're looking for the radius of gyration. All right, so the very first one that we gotta do is you need IG. Yeah, without the IG, it's impossible for us to get it. So therefore, we are going to get the IG. So the IG is the center of mass. Yeah, so the point got to be at GR. Yeah, and that is 1 meter from the point O. Because the point OC right here. Yeah. So first we gotta get the, since you're dealing with the 2 part, the first we're gonna get our rod G. It's gonna right here cut straight in the middle. The plate, all right, got to be 2.5 meter from your point O, because your diameter is only 1 here. Yeah. So in order for the plate to get the center, it's got to be about 2.5. So this is your GP. Yes, which is at the center. So you gotta know like the distance from the center of this circle all the way to O is 2.5, because the 2 is here and 0.5 is your radius. Yeah. So we got GR and GP. And then we will go to the back of our textbook. Yeah, in there you're gonna see your circular plate and rod. All right, and my data is given to you, and we'll just copy that down. Yeah. We know the mass. We put it in. Right here, okay, is your distance. So that's a 2. When we go over the problem, I'll explain that to you, okay, where you get your IG. Is the one that I told you don't worry about it, because I will be giving you, oh, you know, the IG for the rod is this much, you know. So it's we usually get it out from the textbook, depends on the plate or the shape of that. Okay, I'll go back and take a look at that shape, and then we get this, yeah, and then put the mass, of course, and then the distance, which is this guy, yeah. So the formula for IG comes from this. Yeah, here in this case is a 1/4 mr squared, because you're dealing with a circular disc. Here you're dealing with a plate. So here is a 1/12, yeah, and then mr squared. So this is where your IG is calculated, and that is your mass and that is your distance. Okay. Of course, the mass is the same because for the rod is the 2 kilogram, and that's how we calculate. So in the exam, I'm going to give you the IG for the rod, okay? So that way you don't have to calculate this part, yeah? And we have to just plug it in and get this part, okay? All right, we do the same thing here. I'll bring this for you so you know that this comes from here, yeah? Because that's just an IG for this plate. 1/2 comes from the back of the textbook. 4 kilogram, yeah, the same here, mass. And 0 by 5 is from here to here, yeah? This is your distance, so from here, reference point, all the way to here, your D, okay? Because you need the axis in order for you to get the D. And that's just the IG of the plate itself, yeah? So therefore the distance is different here. And then of course you calculate it and you're going to get the mass moment of inertia for your plate. So we have a mass moment of inertia, mass moment of inertia. You add them up together and you get the resultant. Yeah, for the pendulum mass moment of inertia. That's what's it talking about here. Yeah. And after you get all the mass moment of inertia, we can put that. So this is a total one. And we can be able to get the K, which is your radius of gyration. Yeah. So when you go over it, just try to take time. Yeah. And so go little by little. You will get it. Okay. This is just a review. Mass moment of inertia of any body, but its center of mass is always, okay? It's got to be minimum, yeah? It can be 0, it can be maximum. Because you always have a mass moment of inertia, meaning like there is inertia about a center of the mass, meaning this is just a body, by the way. Yeah, you always, but it is at minimum, yeah? Why? Because it is right before the body moves. So it isn't moving, so it can't be at maximum, it's got to be minimum. So your question is like, oh, why it can't be maximum? You can get the MMI maximum at different points, but not at the center of mass. Yeah, center of mass is where you are balancing the body in that position the body is taking in the space. So therefore, it's got to be at the minimum at that point. Okay. Why? Because it gives a way for the body to move, yeah, which is rotation, of course, in the rigid body in this chapter. Yeah, we're dealing with the rotation now. It cannot be 0 because if your inertia is 0, there won't be any kind of resistance to it, so your body won't be there, right? It'll be somewhere else, like bouncing around or just float out. It can be maximum too, because if that's a maximum, it's gonna be like a totally rigid. It won't move. Yeah, there's gotta be there's gotta be some form of the resistance. Yeah, in there in that body at that center, which is the G where the balance. Yeah, balance point for the whole body is, so that your energy transfer can happen upon the exertion of a force on it. Okay. Alright, the second one is if the mass of the body A and B are equal, but their K, yeah, radius of gyration A is equal to, okay, wait, something is, it's just saying like, oh, your mass is equal, so I gotta bring back your equation so you can see. So this one, yeah, so your radius is equal to the square root of IO, and yeah, divided by M, right? So that's your total. So you have your sub MMI down there. So anyway, so mass body A and B are equal, but this, okay, is going to be 2 times of that. Since the mass is equal, yeah, but the K is 2 times of that, all you have to do is just put, right, 2 into here and calculate it, and the mass is going to cancel out each other, yeah, because you're putting this into here like that. Yeah, I can calculate that for you, and you will end up getting C, okay, 4 times because of the square root. So what you have to do is, see, I put the equation for you here, yeah? So you just plug it into here, IA divided by M, and then this one's going to be actually B here, yeah? So I can just write this down for you, B, yeah, divided by M, and this is a 2 right here, yeah? So this M and M is going to get canceled out, yeah, because it's the same thing anyway. So you are going to be left, right, with the square root of IA and square root of IB right in there. So in order for us to get rid of this square root, you will have to balance it. Yeah, that's where your 4 came in. So when you get rid of this square root, yeah, all you have to just square it. Just square this, and square root will be gone, and then square 2, you will get 4. Square the square root, and you will have just a regular, yeah, and you will cancel m together, so you get this. You can do it on paper. Me, I've been doing this all the time, so yeah, I can see through it. Yeah. So anyways, IA is equal to 4IB, yeah, which is this guy right there. Or you have to just plug this in here, time, get rid of the square root, and you will get 4. Yeah, pretty easy. Okay, then we'll get into the translation after we finish the rotation. Alright, that's just showing you how the planning is. This is from your textbook, so after you read that section, I think this is 17.2. Yeah, so you can attempt to do the reading quiz. If you cannot, that's fine too. I will just do it for you. Yeah. So the when a rigid body undergoes translation motion, so you have a body. That thing is moving. This time it isn't rotating. It is moving. Yeah, with a line. Yeah, parallel to each other. So that's your translation motion. The body will not move if you don't have any kind of force applied to it. Yeah, if the body has its own energy, it can move itself autonomous as we are. Yeah, we use our own energy to move ourselves. Object cannot move by themselves unless we equipped it. Yeah, the machine, automated things like that, or put energy equipment on it and AI it so it will go. Yeah, machine learning. So anyways, without that, you gotta move it for it. Yeah, so you gotta need to use the external force in order to move a body. Yeah, in this example, the body is going with a translation motion. So that translational equation of motion, EOM, can be expressed as for. So everything that is moving in motion is always move, right? Measure from the center of mass most of the time, okay? Because in order for us to measure the forces that induce the motion or the body in motion, doesn't matter rotating or translating, you always have to deal with the center of mass on that body, because center of mass is so important to balance that body in a space. Okay, that's why we always go back to the center of mass. So without this, it is impossible for the body to balance itself out with the external forces in the space. Okay, so we call that the translation equation of motion can be expressed for that center of mass in that rigid body. Okay, you won't get it right away. You will have to read and think with it. Dynamics, engineering, dynamics, and statics. Okay, you have to think with it. Otherwise, it won't get into your head. Just by reading, won't get it. Yeah. So, anyways, dealing with the center of mass. And the second one is a rotation, EOM. EOM is nothing, it's just an equation, yeah? Equation of motion, another symbol making you headache. It's just an equation. So this rotation, you can just read it like a rotational equation, yeah, motion. So about the mass center of a rigid body is going to tell you that the sum of the moments due to the external loads, yeah, is equal to this one, of course, yeah. Because we already know, yes, the IG, which is your force, external force, is equal to inertia and angular acceleration. Okay, so therefore, as soon as you talk about and see external load, mean external force, yeah, and that is going to induce the translation motion in that body, and that force is always this, yeah, angular acceleration and this. Because translation, don't forget it, you have two types of translation in there. Yeah, one is going with the parallel, and the other one is going with the curve. Yeah, curve lines. So you still have to deal with the angular acceleration. Okay, application. So let's take a look at the boat. The boat is on a trailer. Yeah, and that is in rectilinear motion. It's a very giant boat. See, look, there's a little tractor right there. So in order to find the reactions, so reaction, action, reaction is always happening between two bodies. There are so many bodies in there, by the way. So in order for us to be visualized on the paper, we gotta draw, yeah, a force diagram. So the force FBD is just an abbreviation for free body diagram. So we're gonna put a boat here, trailer here, and then we're gonna put all of the forces on that boat. So we have weight of the boat, we have normal force, yeah, lifting that, you have 2 points because here, yeah. So those are the balance points. So therefore you have NB and NA, yeah. And then of course you have the your another force because this is your pulling force from here, yeah. So in order for this thing to be in motion, we are giving the energy with this, yeah. The energy comes from the fuel of this tractor. So the tractor is going to move with its own energy, and your human is right there to guide it, yeah, start it. And then you and the tractor move, and when the tractor pulls, your boat in the trailer is going to move. And that force, yeah, external force is right there. And then the balance, yeah. So your G is right there for this boat, okay. So this is your balance point, and it is measured D distance from this axis, yeah, B and A. And then it's been pulled with this force. Force is equal to MA, yeah. And the forces, of course, are measured from this on G. So therefore, we put the acceleration on G. Okay. You, we usually hit the center of mass or point in order to get the resultant force of this. Yeah, because there are little tiny forces all over each point on that boat. They're all different, but they all combine and get this. And we usually figure that out. It came from the center of that boat. Yeah, so that's all about is talking about in this application. But you can't get the idea of where the forces are, what forces are involved, the resultant. When we're drawing that, these are resultant. Okay, this is a resultant. There are so many subforces or subforces out there, depends on the environment. Yeah. So you gotta think, oh, how many equation or motion do we need to solve this problem? What are they? So and so this he is just teasing you. Yeah. Anyways, I give you the answer. There are so many different kinds of forces around it. Yes, gazillion. So people who go to NASA, right, and then study about the different planets and different objects in the space have a difficulty in calculating, right? Because you do not know the environment or the inclusion of the environment up there. So therefore, your calculation is always off. So can we able to master the gravity of different objects, yeah, in the space? We can still master the because we know at least, yeah, the objects or the particles, you name it, in the atmosphere. So yeah, you can set up the space station around the, yeah, around the Earth. We master up to there, yeah. But beyond that, for Mars, right? We're attempting Mars right now. It's a little bit difficult because of the gravity, and the gravity depends. Why? Gravity is your force again. You know, your acceleration. Yes, acceleration depends on the velocity. Velocity depends on the position. Position depends on the stuff. Yeah, your physical stuff, objects, and the object is in the environment. And if you don't know what's in the environment, is yada yada. Yeah, difficult to actually get the accurate value. If you don't have accurate value, you can control, yeah, your stuff to move. Another application right here, and this is your tractor. And tractor is you have a load here, yeah, lift this load up from here, this position to that position. The energy comes from this tractor. So we're doing a curve, yeah, going like down that way. So curvilinear translation. Because this fork is not rotating, okay, it just bang and lift it up, and of course the position is not linear, it's just going down like this way. So if the load, if you're gonna raise it really quickly, yeah, the crate is gonna slide to the left or right. So you gotta think about because see like how the fork, see where the load is, yeah, standing on this fork. So if you don't have like a uniform, yeah, motion, and you're gonna be like having some motion in this crate on that lift. Okay, so if you raise it quickly, it's gonna go a different direction. And we can't say it's gonna go to the left or right by looking at this little 2D, yeah, picture. So it depends on this person who is driving it or lifting it. Yeah, if you balance it like that, it might go. Yeah, it depends on like how he move it. Yes. So what you can do is you can put an object on your hand and lift it up quickly. yeah, and whether it's going to go to the left or right depends on how you move it, how you move your hand up, yeah, and that's what we're talking about here. And how fast can we raise the load before the crate is going to slide? Okay, and these are the things that we will calculate, yeah, when we study this type of motion. So how fast, meaning like how much of the force, external force, are you going to apply, yeah, to this load? And with that force, where this load is going to go, either to the left, right, or how fast can you move, yeah, by keeping this load up there on this fork. If you move it like so fast, it might just like jump out, right? Go all the way to the back. Or it's just like come back down. Yeah, you can't do like that. Of course, even for driving the forklift, you need a forklift certification or something, you know, license or something, because you're dealing with applying the right amount of force to lift this. Yeah, doesn't matter what mass this load is going to be up, and this guy got to pay attention of what is the amount of force I should be giving so that this crate is not going to move left or right and is going to go up, yeah, nicely. So let's see. Of course, most of the tractors are programmed, yeah, on nowadays. Of course, a long time ago it isn't, so you gotta still drive it, yeah, manually controlled. Okay, so now we'll get into the kind of the equations. Yeah, I asked you to write equation because in dynamics, the equation is very important, yeah. We always have to list it up and have our own sheets, otherwise they won't be in your head, yes. It's really difficult to remember and have extensive different symbols and categories, yeah, not just one force. It's just so many categories of force and types of force. I'm gonna stop and record, yeah, a second video because this chapter is too much, yeah. So we will do the second video for this lecture.